Today we are diving into LeetCode problem number 1, toSum. We are given an array of integers called nums and an integer called target. Our goal is to find two numbers in this array that add up exactly to the target, and we need to return their indices. Let's look at this example. Our array is 2, 7, 11, 15 and our target is 9. If we look closely, 2 plus 7 equals 9. So the numbers we need are at index 0 and index 1. Our output should be 0, 1. Simple, right? But how do we write a program to find this efficiently? Using the naive approach or the brute force approach. Imagine first taking the number 2 and checking it with every other number in the array. 2 plus 7. Yes, that matches. But what if the match was at the very end? We would have to compare every single pair. This means we are going to run two loops, loop inside a loop. While this works, the time complexity becomes O(n) square because for n elements we are doing roughly n into n operations. If our array grows to millions of items, this nested loop will completely freeze our system. We need something faster. We need a smart trick. We can do this using a hash map, which in Python is a dictionary. As we loop through the array, we would find the complement simply by subtracting the current number from the target. Complement we need is 9 minus 2 equals to 7. We check our hash map. Is 7 in there? No, it's empty. So we store 2 in the map with its index 2 is to 0. Next we move to 7. The complement we need is 9 minus 7 equals to 2. We check our hash map. Is 2 in there? Yes, it is. We found our match instantly. We look up the index of 2 from the map, which is 0, and our current index is 1. We return 0, 1. Because a hash map lookup takes O(1) constant time on average, we only pass through the array exactly once. This brings our total time complexity down from O(n) square to fast O(n). Let's look at the code. We define a function named toSum with nums and target as parameters. Next, we initialize an empty dictionary named lookup to act as our hash map. We then iterate through the array using a for loop with enumerate, which allows us to get both the index and the current number simultaneously. Inside the loop, we calculate the complement by subtracting the current number from our target. We use an if condition to check if this complement already exists in our hash map. If it does, we instantly return a list containing the index of that complement, which we safely fetch using the .get method, and our current index. If the complement is not found, we store the current number as the key and its index as the value in our lookup dictionary. Finally, if the loop finishes and no matching pair is found, the function returns none. I'm using the .get method here to safely check for the complement's index. If we used standard square brackets like lookup, complement within the square brackets, and that key didn't exist yet, Python would throw a key error and crash our program. But .get method safely returns none if the item isn't found, keeping our code clean and crash-free. Now you might be thinking, okay, this is great for passing a LeetCode interview, but where is this actually used? Let's connect this to a real-world supply chain scenario. Imagine you're building a software interface for an automated logistics warehouse. A delivery truck arrives at the loading dock and it has a strict maximum capacity of 9 tons, our target. Out at sea, a cargo ship arrives and containers are scanned and unloaded onto trucks. We have containers weighing 2, 7, 11, 15 tons waiting in our inventory. If our software uses the brute force, which is the O(n) square approach, to match container weights to fill the delivery trucks perfectly, the system will lag, creating massive bottlenecks at the port. Instead, the warehouse tracking tool uses a hash map backend, a mobile front-end application built in something like React Native, is used by a forklift driver to scan a barcode. The moment they scan a 7-ton container, a quick API request hits our fast API cloud backend. Our O(n) toSum algorithm runs instantly in milliseconds. looks up the database, finds that a matching 2-ton container is already sitting in bay A, and flashes an instruction on the driver's screen. Match found. Pair with container 2 in row A. That is how a tiny, elegant data structure choice keeps global supply chains moving efficiently. It's amazing how a foundational problem like 2-sum scales up to run industrial-grade software. If you found this breakdown helpful and enjoyed seeing how DSA connects to real-world engineering, make sure to hit that like button. Leave a comment with your thoughts and subscribe more for clean coding and architecture breakdowns. Until next time, happy coding!